Hi, thank you for watching. I'll be presenting a theoretical analysis of a specific class of models of the cultural evolution of language. And specifically, we are interested in the question why it is hard to scale up these models. And what we find is that this specific class of computational models is intractable, and that has important theoretical implications for how we interpret the results obtained with these models. Now, this is joint work with this amazing team of collaborators, and I want to start by briefly considering the question why it is important to look at the scalability of our models. Well, in the field of language evolution, researchers are interested in explaining the real-world phenomenon of language. Specifically, a lot of work has been done over the past couple of decades to try and explain properties of natural languages, properties often that are shared between natural languages, as resulting from various constraints and pressures that act on the processes of communication and learning, which are both involved in the process of cultural evolution of language. And this research has been done using both laboratory experiments with human participants, where participants are asked to learn or develop a miniature artificial language, which they then use to communicate, and which is also passed on to new participants entering the experiment who thereby simulate new generations entering the chain of cultural transmission of language. And this research has also been done using computational models, often agent-based models, which simulate the process of cultural evolution of language in the same way, and also often simulate on the same kind of toy scale of having these very miniature representations of languages. Now, to put this into a bit more of a schematic overview, what we're trying to do as a field is to develop a theory as captured by a computational model that explains the real-world phenomenon of natural language. What we found is that laboratory experiments with human participants can capture the properties that we find in natural languages in terms of the patterns of results that come out of these experiments. We've also found that computational models that act on a similar toy scale as these laboratory experiments can explain what dynamics, what constraints and pressures can give rise to these patterns of results that we find in the laboratory. But an important question, if we want to be able to close this loop of theory development, is whether the computational model that we use on a toy scale can, in principle, scale up to the ecological scale of the real-world phenomenon. And what we mean by scaling is specifically in terms of resource requirements. Now, how do we analyze the resource requirements of a computational model? Well, first of all, we need to describe that model on the computational level, which means that we consider a model to be a function that transforms some input into some output. To give an example, if we're modeling learning, then the input might consist of things like a set of observations and a set of hypotheses, and the output might be something like the hypothesis that best explains the data, the observations. Now, if we have such a computational level description of a model, we can think of the resource requirements of a computational model as being sort of the fuel that is needed to perform the computations inside that function. And the bigger the input that is given to the function or the model, the more fuel is needed. Now, the resource requirements, or the resources that are involved in a computational model, are those of time and space. And if we find that the resources required by a given model are more than what is realistically possible, then that should make us question the theoretical viability of our model if ultimately we want to explain a real-world phenomenon which clearly is realistically plausible because it exists. But then, of course, the question becomes how much resources is too much? And to answer that question, we can make use of computational complexity theory, which provides us with formal tools to categorize computational models according to how their resource requirements scale with an increase in the input size. And specifically, this allows us to distinguish between those models that are polynomial time computable, where the resource requirements scale either linearly or quadratically or cubically with the input size, and those models are realistically computable. And we can distinguish those from those models where the resource requirements scale exponentially with the input size, and those models we call computationally intractable. So they cannot be realistically computed for realistic input sizes by any system, be it a brain or a computer, it doesn't matter. Intractability is a principled feature of this computational model. And a formal notion that we use to check whether a model is intractable is NP hardness. So NP hardness means intractable. Okay, now why is this intractability or tractability important? Well, we know that the real-world phenomenon that we're trying to explain has to be tractable simply by virtue of the fact that it exists. So, because natural languages exist, they have to be tractably learnable, tractably usable, and tractably evolvable. Now, if we'd find that the computational model that captures our theory that we use to explain this real-world phenomenon, if we'd find that that computational model is intractable, that has two consequences. One being that we now know that the computational model can, in principle, not scale up to the ecological scale of the real-world phenomenon. And the second consequence is that our intractable model that captures our theory cannot explain the real-world phenomenon exactly because the real-world phenomenon has to be tractable simply by virtue of the fact that it exists. Now, now that we have that theoretical background, we can look at our specific case study, which is models of the cultural evolution of language. And we specifically focus on a class of models that is known as iterated Bayesian language learning models. And these models have been widely used in the field of cultural evolution of language ever since 2007. And the fact that these models use Bayesian inference as a model of learning comes with the advantage that it gives modelers minute control over what learning biases they give to their individual agents in the model. And that allows modelers to separate out the influence that an individual learner has on kind of shaping the language as a result of their individual learning biases, to be able to separate that out from the cumulative effect of cultural evolution of language over many generations. Now, something that struck us when we looked at existing iterated Bayesian language learning models, and also when we used these models ourselves, is that these models always use very small languages. So here are some examples. A lexicon of 4 signals by 4 meanings, 3 signals by 3 meanings, and that is virtually microscopic if we compare it to the actual vocabularies that adult humans know, which consist of tens of thousands of words. So this observation, of course, made us wonder about whether these models can be, in principle, scaled up to this more ecological scale, and in other words, whether these models are tractable or not. Now, in order to analyze the tractability of a model, we first need to have a general formalization of this entire class of models. So our general formalization captures various specific instantiations of specific models. And our formalization consists of 3 parts: language, learning, and evolution. And I will show you how we formalize each of these parts in turn. To start with language. So as a model of language, we use a mapping between signals and reference. In other words, we formalize a language as being a lexicon. And given this model of language, what a learner has to do is to find what the mapping is between these signals and these reference. And in order to do that, a learner receives observations, receives data. And specifically, we assume that, following existing models, we assume that learners receive data from a sort of helpful parent who not only produces signals, but also points out with each signal which referent they intended. So the observations that a learner receives consist of signal-referent pairs. And because we're assuming Bayesian inference as a model of learning, following this existing class of models that we're interested in, a learner has to consider the entire space of possible lexicons and find which lexicon best fits or best explains the data they observed. Now, the final step in our formalization is the formalization of evolution. A learner, as I said, receives observations, and specifically they receive these observations from an agent from the previous generation in their population. And each learner then performs Bayesian language learning, so Bayesian inference, on these observations in order to infer a lexicon which they themselves then will use to produce data for the next generation. Now, a parent agent, the parent agent who produces data, has, aside from their lexicon, also a production model which determines how likely they are to use a given signal for a given intended referent. They have a set of intentions that they want to convey. And we also allow, again, following existing models, for the possibility of production error. So some small probability that a speaker produces a signal that's slightly different from the signal they intended. And finally, we also allow in our general formalization for the possibility of adding fitness-based selection, which means that we can set the model in such a way that agents from the parent generation are selected to be allowed to transmit data or produce data for the next generation, depending on some fitness measure. Okay, now that we have our formalization complete, let's have a look at what we found in terms of the computational complexity of these models. We found, first of all, that Bayesian language learning is NP-hard, so it's intractable, and that has as a consequence that Bayesian language evolution is also NP-hard, because Bayesian language learning is a sub-process of Bayesian language evolution. And we found that these two models or steps in the process are intractable even if we constrain the input domain in certain ways, such as restricting or constraining the input domain such that there's only one type of agent, and each learner receives only one observation, and when the prior and the production model are themselves polynomial time computable. So the intractability is not hiding in the prior or the production model. Similarly, we can constrain the input domain of Bayesian language evolution such that the population consists of only one agent, and all parent agents only communicate one intention. And again, the prior and the production model are polynomial time computable, and even then, Bayesian language evolution is still intractable. Now, what does this mean? Well, we have some bad news and some good news. Bad news is that we now know that these simulations run with this specific class of models fundamentally cannot go beyond the toy scale. Theoretically, it means that we cannot take it on faith that the effects, so the patterns of results that we observed in these toy scale models, would scale up if we use more real ecological scale real-world lexicons. It also means that even if those large-scale effects would exist, our theory, as captured by this specific class of computational models, cannot explain them because we know that the real-world phenomenon has to be tractable, and we found that our computational model is not tractable. Luckily, we also have some good news. So in general, as researchers in the cultural evolution of language, we aim to explain universal properties of language through the constraints that are imposed by the evolutionary and cognitive context. And we can think of tractability of learning and evolution as also being universal properties of language. And they too can be explained by constraints. Now, luckily, there's an existing method, which is the method of parameterized tractability analysis, that allows us to face this issue of scaling head-on, because it can guide us in the process of identifying plausible constraints under which the model is tractable. And with that good news, I want to leave you. Thank you very much.